Welcome to this explainer. Okay, today we're looking at a scenario that literally sounds like it was ripped straight from a sci-fi heist movie, but it is happening right now in modern physics labs. We are unpacking a groundbreaking, highly revealing paper by Jaime Moreno and his team of researchers. What they've done is expose a massive, fundamental vulnerability in the way we verify quantum technology. We're going to walk through their exact findings step by step, and I promise you by the end, you'll see exactly why the quantum physics community is losing sleep over this.
So let's just dive right into the core question at the heart of this paper. What if the greatest superpower of quantum computing could be completely faked? This single question transforms a dense academic physics paper into a thrilling technological warning. Think about the billions of dollars and decades of research pouring into quantum tech right now. We place absolute trust in the promised power of our future quantum devices. But if the core mechanism making them powerful can be spoofed without us even realizing it, the entire foundation of quantum information security is brought into question. It's kind of like building the most impenetrable vault in human history, right? Only to discover the biometric lock can be bypassed with just a photograph.
Section 1. The Quantum Baseline. Understanding the Entanglement Promise.
Now, as we all know, quantum entanglement is the absolute foundation of our future capabilities. It's the central resource underpinning all these emerging technologies. We aren't going to rehash the basics of spooky action at a distance. You already know that when we talk about quantum computers doing things that our current, classical computers simply cannot do, entanglement is the secret sauce making that possible. But here is why the stakes in this paper are so incredibly high. Entanglement is notoriously fragile. It degrades with the slightest environmental noise, which means verifying that a system is truly entangled in a practical, messy, physical setting is historically a total nightmare. If you don't definitively have entanglement, well, you don't have a quantum advantage. You really just have a very, very expensive room heater.
We're all expecting this massive leap in computing power, moving from standard classical systems to true beyond classical capabilities. And the bridge getting us there? It's entanglement. But here's the catch. That leap relies entirely on our ability to definitively prove that the systems we are building are actually entangled. If our verification methods are blind to certain tricks, we might think we've achieved quantum supremacy, when in reality, we're just stuck with classical capabilities dressed up in some fancy math. The implications here are huge. We are talking about the potential for researchers and massive companies to waste years of development and millions of dollars acting on false positives, simply because their verification methods were telling them exactly what they wanted to hear.
Section 2. A flawed theoretical assumption. The illusion of perfect measurement.
Okay, we really have to examine this dangerous disconnect between theoretical models and real experimental implementations. Physicists love to joke about the spherical cow in a vacuum. You know, that tendency to create mathematically beautiful models that completely ignore the messy friction of reality? These theoretical models for quantum verification rely on a massive assumption. They assume that quantum measurements can be realized perfectly. But step into any real physical lab. It's dusty. Things vibrate. Lasers drift. The authors point out that as the complexity of a quantum system grows, assuming exact, flawless measurements becomes incredibly unrealistic. This causes a widening mismatch between what the pristine theory dictates and what the chaotic physical experiment actually does. And where there is a mismatch, there is an exploitable loophole.
Which brings us to Section 3, Faking the Quantum Connection, the Hack Revealed.
0.23%. That's it. That is the entire measurement fidelity error the researchers needed to completely break the system and fake an entangled state. Let that sink in for a second. Usually, when we think of sabotaging a highly advanced piece of technology, we picture someone taking a sledgehammer to a server rack or, introducing a massive glaring glitch. But Moreno and his team, they acted like white hat hackers. They didn't need a massive deviation. They only needed an error margin of less than 0.25% to pull off this quantum heist. I mean, it is almost absurdly small. Think of it like a master illusionist performing on stage. The audience, which in this case is the brilliant scientist trying to verify the entanglement, they're looking at an apparatus that is 99.77% perfect. To any rational observer, that looks like an incredibly precise, reliable measurement device. But the illusionist knows exactly where the blind spots are. An attacker can take that imperceptible 0.23% sliver of adversarial error, operate entirely in its shadows, and use it to completely fake the quantum magic. The researchers realized they could exploit that tiny gap between perfect theory and physical reality to literally trick the machine into seeing something that just isn't there. So, we can break down this hacking attack into a pretty clear three-step playbook. Step 1. Introduce arbitrarily small measurement errors into the environment, like that 0.23% we were just talking about. Step 2. adversarially encode those errors right into the measurement apparatus itself, essentially weaponizing the slight imperfections of the hardware. And step 3 is where the real audacity lies, the grand finale. The device falsely certifies high-dimensional entanglement in systems that are in fact entirely separable. They're taking systems with absolutely zero quantum entanglement and successfully passing them off as highly complex entangled states. It's literally the physics equivalent of passing off a printed piece of paper as a certified, flawless diamond, and the jeweler's own magnifying glass is confirming it.
Section 4. The tiny measurement hack. Testing the exploit.
Right, so we know the theory behind the attack, but how did the authors actually pull off this quantum heist in physical reality? First off, they didn't even use fragile quantum states to fake it. They utilized classical photonic states. Second, they encoded this illusion in the spatial degree of freedom. And third, and you really have to appreciate the sheer experimental flex here, they successfully spanned up to 61 dimensions. For anyone who follows quantum computing hardware, you know scaling up dimensions is computationally massive and just incredibly difficult to stabilize. 61 dimensions is a staggering level of complexity. The researchers proved that even at this highly advanced, high-dimensional level, the false certification still worked perfectly. The machine confidently lied to them across 61 different dimensions.
And the researchers, they didn't mince words about the gravity of this. They stated, "Our results uncover a fundamental vulnerability in current methods for high-dimensional entanglement detection." I mean, that is the kind of quote that sends a chill straight down the spine of hardware developers. They aren't just saying, hey, we found a quirky bug in one specific machine in one specific lab. No, they're pointing to a systemic shockwave. It is a fundamental vulnerability in our current methods overall, meaning that virtually every team currently relying on these standard verification protocols might need to go back and completely rethink their hardware security from the ground up. Which leads into Section 5, Securing Our Quantum Future, the Consequence and Fallout.
There's a really deep irony here that we have to confront. Complex quantum devices are highly susceptible to small adversarial perturbations. We naturally tend to think that as our tech gets more advanced, more robust, more complex, it inherently gets better and more secure, right? We assume a larger vault is a safer vault, but in the quantum realm, the exact opposite paradox is playing out. As these machines scale up, adding more qubits and higher dimensions to perform world-changing calculations, their attack surface actually expands. They become more vulnerable to these infinitesimally small adversarially encoded attacks. The smarter the machine gets, the easier it might actually be to trick it with a fraction of a percent of error.
So this leads us to the ultimate, really urgent call to action from Moreno and his colleagues. We urgently need secure verification of quantum information that is robust to bounded discrepancies between theory and experiment. And why does this actually matter to you? Because if we're going to rely on quantum systems in the next decade for, say, unbreakable national security communications, or designing life-saving medical breakthroughs, or running global financial encryption, we simply cannot afford to be naive about lab realities. We can no longer blindly trust mathematical assumptions of exact measurements. We absolutely have to design verification tests that acknowledge the messy, imperfect reality of the physical world.
A mere 0.23% error. That is enough to fabricate the very foundation of quantum computing. And it forces us to ask a pretty critical question. Can we really build a secure quantum future if we can't even trust our own measurements? We clearly have a massive amount of work to do to bridge the gap between brilliant theory and secure reality. Thank you so much for joining me to unpack this fascinating paper.